Hello everyone, I am Abhishek Datta and you all are watching my YouTube channel Mathematics Made Easy. Today in this video, I am going to discuss about the consistency of a system of linear equations by Cramer's rule. In my previous video, I have discussed the method of solution of the same with Cramer's rule, with the help of Cramer's rule. Now today I shall be discussing the conditions of consistency of the system by the same method, that is Cramer's rule. Now as you all know, by consistency we mean that whether a system of equations is solvable or not. If we can find at least one solution for any system of equations, at least one solution we can find, then such a system is said to be consistent or solvable, else the system is known to be inconsistent. That is, we cannot find any solution for the system. So as we are discussing about a linear system, let us discuss by taking three variables. So a linear system involving three variables are given by a1x plus b1y plus c1z equal to d1, a2x plus b2y plus c2z is equal to d2, a3x plus b3y plus c3z is equal to d3. And we have already discussed in my previous video how to solve this system by the Cramer's rule. If you remember, in that video, you can also check my video, we formed four determinants, namely d, that is the coefficient determinant, and other three determinants dx, dy and dz, where dx, dy and dz are formed from d by replacing the first column, second column and third column of d respectively, as the variables x, y and z respectively occurs in the first, second and third column of the system. And finally, the solution was given by x equal to dx upon d, y is equal to dy upon d and z is equal to dz upon d. This was the solution to the system. Now let us discuss the conditions under which such a system shall be consistent or it may become inconsistent. So for that, first we have to find the coefficient determinant d itself. So if we find the value of d, two cases may occur, that either d becomes equal to 0 or d becomes not equal to 0. Either we can have a non-zero value for d or d may be equal to 0. Either of these two cases will occur. No other no other case is possible for d, because the value of a determinant is a real number in this case, because we are dealing a real system. So either this will be 0 or this should be non-zero. Now if the value of d, that is the coefficient determinants, becomes non-zero, then this system will be consistent, that is solvable and having a unique solution. So under this case, when d is non-zero, the system is consistent. We shall have a consistent system having unique solution. So here we have a consistent system having unique solution set. So what we mean by unique solution set is there will exist exactly one value of x, exactly one value of y and exactly one value of z. That is exactly one triplet x, y, z, which shall satisfy all the three equations simultaneously. So for that, the condition should be the coefficient determinant must be non-zero. Now what if d becomes 0? On the other hand, if the coefficient determinant becomes 0, then two cases may possible. The system may be consistent or it may be inconsistent also. So here two cases are possible, that apart from d equal to 0, if all the other determinants, other three determinants dx, dy and dz also become 0. That is, if all the 4 determinants become 0 simultaneously, all these 4 become 0 simultaneously, then the system should be consistent, but it shall have infinite number of solutions. So, under such a case, we shall have a consistent system but having infinite number of solutions. That is, we can find infinitely many triplet x, y, z which will satisfy all the 3 equations simultaneously. On the other hand, if together with d equal to 0, at least one of dx or dy or dz becomes not equal to 0, that is with d equal to 0, if at least one, at least means exactly one may be non-zero, or exactly 2 of them may be non-zero, or all 3 may be non-zero. At least means minimum. If minimum one of these 3 dx, dy, dz becomes non-zero, it may so happen that 2 of them are 0 but 1 is non-zero, then also the system will be inconsistent. Under such a case, we shall have an inconsistent system. Which means there would be no solution to this system. We cannot find any triplet x, y, z which will satisfy all the 3 equations simultaneously. So, here we have the condition for consistency under Cramer's rule, which states that a linear system of equations can either possess a unique solution or it can possess infinite number of solutions, or it can have no solution. So, this is the important point to note, that whenever we have a linear system, the number of solutions will be 0, that is inconsistent, there is no solution at all, or exactly one solution set, that is exactly one values of x, y and z, or if more than one, the number of solutions will always be infinite. There cannot be 2 or 3 or 4 solutions like that. If we have more than one solution set, that should be always infinite in number. And we can also explain the same concept geometrically. Geometrically, these 3 equations represents planes. We all know that a linear equation in 3 variable x, y, z, a equation like this, ax plus by plus cz is equal to d, represents as plane in 3 dimension. So, when d becomes non-zero, then we have 3 planes intersecting at a single point only. As if we can imagine a box, if we have a wooden box, that is a cuboid, and if you consider any 3 adjacent walls, say if you consider the roof, this wall and the wall adjacent to this, if you consider any 3 adjacent walls, then you can see that these 3 planes meet at one point only. So, solution means a point which is common to all the 3 planes. So, when d becomes non-zero, geometrically we have 3 planes intersecting at one point only, that is we can compare the situation with any 3 adjacent walls of a cuboid. So, there will be only one common point, one common vertex to all these 3 walls or all these 3 planes. So, that vertex gives us this unique solution. Now, what happens if d is 0 and at least one of dx, dy, dz becomes non-zero? Under such a case, we shall have 3 parallel planes. These 3 planes will be parallel to each other, and between 3 parallel planes there is no common point. As we all know that a solution to a system means the point should be common to all the 3 loci. So, if we have 3 parallel planes like this, so they will have no points in common, so the system becomes inconsistent. So, for this condition, geometrically they represent 3 planes parallel to each other. and for the infinite number of solution, we have the three planes coinciding with each other. When all the three planes coincide, so every point on them becomes common to the entire system, and we have infinitely many points on a plane. So this system shall possess infinitely many solutions. So geometrically, a linear system possesses a unique solution means we have three adjacent planes, or we have three adjacent walls of a cuboid intersecting at one common vertex. A linear system possessing no solution means, this one, no solution means we have three parallel planes having no point in common, and an infinite system representing, a linear system having infinite number of solution represents three planes coinciding with each other. And or there can be another implication also, either the three planes will coincide or they will have a common line of intersection. Likewise, if you consider 3 pages of a book, 3 consecutive pages of a same book, so those 3 pages will have the same common line of intersection, the line from where the pages are connected to each other. So we can have that case also for an infinite number of solution, either the 3 planes will coincide or they can have one common line of intersection. So every point on that line shall represent a solution to this system, and we can have infinitely many points on the line. So this system will possess infinite number of solutions. So this is the discussion on consistency of a system of linear equations with the help of Cramer's rule, and we can extend the same for a linear system having n number of variables or n number of unknowns. There we shall have the coefficient determinant d and dx1, dx2, dx3 up to dxn for the n variables x1, x2, xn, and the same rule applies that if d not equal to 0, we have a unique solution. If all the determinants become 0, we have infinite solution. With d equal to 0, if at least one of dx1, dx2 or dxn is non-zero, the system becomes inconsistent. So in our next discussion, we shall be discussing some more methods and consistency rule for solving a system of linear equations. I hope this video is helpful to you. If you have any doubts, you can ask me in the comment section, and if you like this video, if the video is helpful to you, please like my channel and subscribe my channel. That will help my channel to grow. Thank you all for watching. Have a nice day.